the theory of grand unification of the forces of the universe. You might have seen that some time ago, Terrence Howard, an actor who played in the Iron Man and had some other roles, went on Joe Rogan's, one of the most popular podcasts in the world. For more than 3 hours, he wasn't talking about his acting career. He was explaining his own theory of how the universe works and the mathematics he claims to have invented. For example, according to him, 1 times 1 equals 2? In terms of sheer strangeness, another of his statements might top even that. At one point, he casually mentioned that when he was about 7 or 8 years old, he knew the equation for a grand unified theory. So why didn't he share such an important knowledge with anyone? Because he forgot it. Anyway, whether Terrence Howard is just not so subtly trolling, genuinely believes it, or maybe dealing with something else, a celebrity diving into conspiracy theories and pseudoscience. Feels like I've seen that before. This is to say that such a grand unification that Howard just forgot, damn him, is something that scientists have been trying to achieve for decades. I'm not even talking about the theory of everything right now, which I'm sure most of you have heard of, and which we may not be able to develop at all. I mean, so to speak, a step that comes before it. We'll talk about that in more detail today. Today we'll talk about the attempt to unify 3 of the 4 fundamental forces or interactions of the universe: electromagnetism, the strong and weak nuclear forces. What if 3 seemingly very different fundamental forces are actually one and the same? What does it mean for forces to unify into one, or to be manifestations of a single great force of the universe? How could that happen? If the forces were unified, how would that affect us? All of this might not be very intuitive, so let's try to figure it out together and at least get closer to understanding what a grand unified theory actually is. I'm Andrei, and this is Cosmos Elementary. Not long ago, I already made a video about the main forces of the universe, or more precisely about the fundamental interactions. But back then, I was addressing a different question. For convenience and brevity, today I'll occasionally refer to interactions as forces. Today it is believed that there are 4 fundamental forces governing the universe, thanks to which everything we see around us exists and functions. Gravity governs objects with mass. The formation and motion of planets, stars and galaxies keeps the atmosphere and us from flying off into space, and so on. Electromagnetic interaction depends not on mass, but on charge, and it acts between charged particles. It governs magnetic and electric fields and helps electrons and atomic nuclei stick together. Thanks to it, chemical reactions occur, friction works, and many other things happen. If electromagnetism prevents atoms from falling apart, then the strong nuclear force prevents the nuclei of atoms, made of protons and neutrons, from disintegrating, as well as the protons and neutrons themselves, which are made of quarks. The weak interaction is probably the most obscure of the 4. Most often, you'll hear that it's responsible for certain types of nuclear decay, which is very important of course, but it definitely doesn't sound as epic as in previous cases. You could also say that it is responsible for the interaction of subatomic particles. Besides decay, it also plays a role in fusion reactions, and it is the only force that can transform one particle into another. That's all very brief. I've talked about interactions in more detail before, but we'll touch on some aspects again today. But what if at the moment we've only discovered 4, when in reality there are more? I actually talked about the idea of a possible 5th force of the universe and what it might be in a separate video. Today, in a sense, we'll go in the opposite direction, not by increasing the number of forces, but rather reducing them, or more precisely, by unifying them. We humans always want to simplify things, and that's understandable. We want to believe that the universe, which seems complex and confusing to us with all its interactions, a bunch of particles, phenomena, and laws, is, at a deeper, more fundamental level, actually simpler. That the various processes which seem to us completely unrelated are actually governed by a single mechanism. And if we find this mechanism, we'll understand the universe more deeply, and who knows, maybe even find a way to use it. It would be amazing to have not a complex jumble of laws, but a set of simple rules that could explain absolutely everything we observe in the universe. In the history of science, such simplifications or unifications have happened more than once. A good early example of this is what Isaac Newton did. For centuries before him, people didn't connect the motion of planets with what happens on Earth, why things fall. Newton, however, proposed a single explanation for both: the force of gravity. In my recent video about quarks, I talked about how scientists in the 20th century kept discovering more and more new particles, which made our picture of the world more complicated. And for a while it was impossible to build a coherent logical framework out of this so-called particle zoo. But then quarks were discovered and everything fell into place. Another example of unification is Einstein's theories, in which he combined the concepts of space and time into a single space-time, which were previously thought to be independent. An example very close to today's topic is one of the major achievements of James Clerk Maxwell. After all, one of the fundamental interactions that we are trying to unify today was not always a single force in our understanding. Of course, I'm talking about electromagnetism. We were finally convinced of the unified nature of electricity and magnetism thanks to Maxwell's work. In short, many things that were once considered completely unrelated processes and phenomena are now unified. Moreover, many of these discoveries not only represented huge leaps in our understanding of the universe, but eventually, well, often not immediately though, led to technological breakthroughs. So it's quite logical to ask, what if, like in those past examples, what we have now isn't the final picture of the world, and could we unify further? That's entirely possible, and there has already been some progress. In popular articles, videos, and books, the focus is usually on the notorious theory of everything, a theory that would unify all four fundamental interactions. But there is a big problem with that. Gravity, you heartless, you know who. Gravity currently stands apart from the other three forces because, unlike electromagnetism and the strong and weak interactions, a full quantum description of gravity doesn't exist yet. For the three interactions, carrier particles have been discovered. For gravity, there aren't any. The graviton remains a hypothetical particle for now. Complete and widely accepted quantum theory of gravity doesn't exist yet. There are attempts to create one. There is something like loop quantum gravity, in which spacetime itself is made up of tiny components, loops. String theory can also be included here, but the current candidates for a quantum theory of gravity are still far from reaching the same level as general relativity or the standard model of elementary particles. In short, unifying gravity with the other interactions, or combining general relativity with the standard model, what is often called the holy grail of science, and usually referred to as the theory of everything, hasn't been achieved yet. But the other three forces are already, you could say, written in the same language of quantum mechanics. The three forces are described by the standard model, and their unification is, in a sense, closer to reality. Moreover, two of the three forces have already been successfully unified. This unification of electromagnetism, the weak and the strong interactions into a single superforce is what's called the grand unified theory. But how do you actually do this? And what does it even mean? The topic of grand unification is actually very complex, like pretty much everything related to quantum stuff. There's a lot of mathematics, equations, and various nuances that we won't cover today. Still, I'd like to build an intuition that goes a little deeper than just forces merge. I've already described the main functions of the three interactions. They seem quite different both in how they act and in other properties. If you bring gravity into the picture, it only ever attracts. You could say it has only one type of charge: mass energy. Electromagnetism has two types of charge: negative and positive, and this force can both attract and repel. The strong interaction actually has three types of charge, which are called color. Naturally, this has nothing to do with the color we're familiar with. It's more of a convenient analogy. The way these colors work is more complicated though. The three interactions differ in the number of their carrier particles, which are also called gauge bosons. This is usually described like this: particles involved in a particular interaction exchange carrier particles. For example, quarks inside a proton exchange gluons, which hold them together. The number and properties of these gauge bosons also differ for each force. Looking at the standard model table, it may seem like there are only 4 gauge bosons, but in reality there are more. For electromagnetism, there is just one particle, and it is massless, the well-known photon. For the weak interaction, there are 3 particles, the neutral Z boson and 2 W bosons, one negative and one positive. Both W and Z bosons are very massive. For the strong interaction, the carrier particles are gluons. There are actually 8 of them, and they differ in their combinations of color charges. Gluons, like photons, are massless. Another obvious difference is the strength and the range over which these interactions operate. The weak interaction is the weakest of the 3. Next comes electromagnetism, while the strong interaction is roughly 100 times more powerful than electromagnetism and many orders of magnitude stronger than the weak force. Next, electromagnetism acts over any distance, or you could say infinite distances. On the other hand, the weak and strong forces act over extremely short distances. The strong interaction essentially disappears beyond the distance of about 10 to the power of minus 15 meters, roughly the diameter of a proton. The weak force acts over even smaller scales, no more than 10 to the power of minus 18, which is 1000 times smaller than the range of the strong force. Yeah, it's a bit of a mess. The number of force-carrying particles is different, their properties differ, the strength of the interactions varies, the range is different. All of this sounds like a problem for unification. After all, in simplified terms, if all 3 forces were to become a single force, they would have to have the same strength and share the common set of carrier particles. Here we can again recall the example of how electricity and magnetism were unified. They seemed like completely different phenomena, yet at their core lies the same carrier particle, the photon. But in the current situation with the 3 forces, we don't see anything like that yet. On the other hand, it's possible that we don't observe this under the ordinary conditions we're used to. But under different conditions, the forces come closer together. And in principle, that's probably how it actually is. Still, besides the differences, there are also some hints of a connection between the fundamental interactions. For example, the same particle can be affected by several forces at once. Quarks are affected by all 4 fundamental interactions. Some leptons, like the electron, are affected by electromagnetism and the weak interaction. The other half of leptons, like neutrinos, are electrically neutral, so electromagnetism does not affect them. Many of you have probably heard the phrase neutrinos interact weakly with matter. And this not only means that these interactions are rare, but primarily that they occur mostly through the weak nuclear force. Although, since they also have mass, gravity affects them too, but their mass is extremely small. In general, several forces can act on the same particles at once. Another hint of a deeper connection can be noticed if we look closely by analyzing this table and the properties of the particles in it. If we look at all the charged particles, we'll see that besides being either positive or negative, their charges are either 1, 1/3, or 2/3. I recently talked about the story of fractional charges in the quarks video, but here the peculiarity is a bit different. Let me remind you that the charge of 1 is not just 1. It equals the value of 1 elementary electric charge, which is approximately 1.602 times 10 to the power of minus 19 coulombs. Why is that for all charged particles, their charge is either equal to this value or to the same fractions of it? As a result, the sum of the charges of the quarks that make up a proton equals 1, which balances with incredible precision the charge of the electron minus 1, ultimately allowing neutral atoms and everything we see around us to exist. Even the gauge W bosons of the weak interaction have a charge of either +1 or -1. One might think that the charge of some particles doesn't have to be just 1 elementary charge or fractions like 1/3 or 2/3. And the fact that such different particles share this pattern might hint at a deeper structure, a unifying mechanism pointing to a possible grand unification within the standard model. But that's not all. Another key hint for the possibility of grand unification is the strength of interactions. You might say, wait, didn't I just categorize this property as something that differentiates forces rather than unites them? Yes, but here's the trick. The important point for unifying interactions is the situation where their strengths become equal. And right now, that's clearly not the case. But the question is, has it always been this way? Or could there be conditions under which these forces become equal? We're measuring the strength of each interaction under normal conditions, everyday energies or temperatures. And as we've already seen, these forces differ by orders of magnitude. But what happens if we start increasing the energy? Scientists have actually calculated this. They used known values and special mathematical tools and discovered something very interesting. As the energy increases, different forces behave differently. Electromagnetic interaction weakens, while the weak force, on the contrary, becomes stronger. We can create a graph with energy on one axis and the strength of the interaction on the other, and plot curves showing how the strength of the interactions changes as energy increases, according to modern calculations. Electromagnetism weakens while the weak force strengthens. Can you guess where this is heading? If the trend continues, at some point they will meet, and their strength will become equal. And in this case, they are said to unify, forming a single electroweak interaction. And today it is said that the unification of electromagnetism and the weak nuclear force has been confirmed. But how was this achieved? We've already discussed the similarities and differences of the three forces, but if we focus only on the two that have already been unified, the story repeats itself. Scientists noticed some similarities and connections between electromagnetism and the weak interaction a long time ago. For example, many particles experience both interactions. And since the 1960s, scientists have been actively working on the electroweak theory. This theory made certain predictions that could be tested even with the technology of that era. The electroweak theory specifically predicted the force-carrying particles for the weak interaction, the very W and Z bosons that we now see in the standard model table, and it predicted particles with specific properties. Often when particles change their identity as a result of the weak interaction, their charge changes as well. For example, if a neutral neutron, so to speak, decays, a positively charged proton appears. However, the electroweak theory also predicted interactions in which the charge didn't change, known as the neutral current. The neutral current had to be associated with a neutral particle, the Z boson. And in the early 1970s, scientists tried to detect this neutral current using a special detector, a bubble chamber installed on the proton synchrotron particle accelerator at CERN. The chamber, called Gargamel, was a tank about 5 by 2 meters, or about 16 by 7 feet, weighed 1,000 tons, and held 12 cubic meters of heavy liquid freon. Charged particles leave tracks in the liquid inside the chamber, and from the nature of these tracks, one can determine the properties of the particles. Neutral particles don't leave tracks, but particles produced after interactions of neutral particles with others do, and by analyzing these tracks, it's possible to reconstruct what happened. In 1973, signs of the neutral current were detected. Here is a photo of the discovery from the bubble chamber. On the left are the actual data, and on the right the explanation. You can see the track patterns in the right part of the image. The dashed line shows the invisible path of the neutrino, which leaves no track. At this point, the neutrino collided with an electron, producing photons that in turn created electron-positron pairs. And we see the tracks from these particles. After similar experiments were conducted by the Harvard, Pennsylvania, Wisconsin Fermilab collaboration, traces of neutral currents were also observed, and their existence became widely accepted. And this was the first important step toward the experimental unification of electromagnetism and the weak interaction. By the way, if you ever happen to visit CERN, you can even see the legendary Gargamel chamber with your own eyes. It's now on display as an exhibit. The success of discovering the neutral current led to the proton synchrotron being converted into a proton-antiproton collider. And this eventually led to the more direct discovery of both Z boson and W bosons precisely with the properties and mass ranges predicted by the Electroweak theory. In other words, the carrier particles of the weak interaction were predicted by a theory that treated electromagnetism and the weak force as manifestations of a single unified interaction. And in the end, these predicted particles were discovered in experiments. And that's why it's now believed that they are indeed different manifestations of a single force at low energies and that they unify into one force at higher energies. The electroweak force should have 4 force-carrying particles, and when they act as a single force, all of them are massless. Interestingly, under normal conditions, only the photon is massless. This means that there must be some mechanism that, when 2 forces separate, gives mass to the 3 of the 4 particles. This happens during the so-called spontaneous symmetry breaking. In fact, everything here is very closely related to symmetries, but I'm intentionally not diving into them for now. We might talk about them separately another time. So, has anyone guessed the mechanism that makes 3 of the bosons massive? Of course, this is the famous Higgs mechanism. And that's why the discovery of the Higgs boson was so significant and, as they say, finally completed the Standard Model. So it turns out that we've already unified 2 of the 3 forces. Looks like it. And for the grand unified theory, there is still 1 left. It's a bit more complicated though. Let's return to our graph where we saw the unification of electromagnetism and the weak interaction. What happens next to the already unified electroweak interaction as the energy increases further? It continues to evolve and increases slightly. And what about the strong interaction? The strongest fundamental interaction, the strong force, weakens as energy increases. And in the end, according to modern calculations, all 3 forces converge at a single point. This may not be a coincidence, and this fact strongly hints at the possibility of grand unification, that at very high energies, all 3 forces become one. But here's the thing, I'm talking about very high energy. How high exactly? Well, in this graph it is shown that all 3 forces meet at an energy of 10 to the power of 15 giga electron volts. It's worth noting that there are many forms of grand unified theories, and the details can vary. But in general, they usually talk about energies around 10 to the power of 15 or 10 to the power of 16 giga electron volts. If I talk about the corresponding temperature, it would be extremely hot. About 10 to the power of 28 kelvins. That's 10 octillion degrees. If we wanted to directly prove such a unification, we'd have to create these conditions in a laboratory, and we simply cannot do that yet. There are estimates that achieving this would require a collider, well, slightly larger than the LHC, a diameter of roughly about 1000 light years. Yeah, which is why direct confirmation of the grand unification theory is for now just a bit beyond our reach. However, we can also recall that in the very first moments of the universe, it was extremely hot, and today it is believed that roughly 10 to the power of minus 35 seconds after the beginning of the expansion, the universe was so dense and so hot that the 3 interactions were unified. But soon after, as it cooled, they separated. First, the strong force separated, and then the electroweak force split into electromagnetism and the weak interaction. So does this mean that for now we can only build theories about grand unification and can't experimentally confirm the nature of these 3 forces? Not exactly. There are actually some possibilities here that don't require building a collider the size of a part of a galaxy. Just as the electroweak theory predicted the existence of specific particles, grand unified theories predict proton decay. Some particles are stable and they exist for a very long time and don't decay, while others decay quickly. As far as we know, the proton is very stable. We can't say that it never decays, but we are quite confident that its average lifetime is extremely long, many orders of magnitude longer than the current age of the universe. Why are we so confident about this? Well, at the very least because we are alive. You might think that if the proton could decay, it would mean that we and everything around us couldn't exist, because the particles that make up everything would fall apart into pieces. But for this to happen, the proton's lifetime would have to be much shorter. Even if on average a proton lived, say, a billion years, it would still be catastrophic for us. Why? When we say that a particle's lifetime is billions and billions of years, it doesn't mean that all the protons in our bodies will live that long. So there's nothing to worry about. A particle's lifetime is probabilistic, which is why I made the distinction earlier and said average lifetime. Individual particles can live much longer than the average, while others much shorter. And with a lifetime of, say, a billion years, considering how many particles are in our bodies, enough of them would decay to cause radiation-induced cancer in everyone. So the proton's actual lifetime must be much longer than that. Still, scientists would like to make at least a rough estimate of what a proton's lifetime could be. For this, you need much more matter than in a single human body. For example, you could take several thousand tons of water, place it in a chamber deep underground, and isolate it as much as possible from external radiation. Install detectors that would register the characteristic macroscopic flashes of radiation expected from proton decay and wait. Such experiments have been conducted since 1980s. They became more complex and refined over time, but to this day, none of them have detected a single proton decay signal. This doesn't mean that protons never decay, but at the very least, we can say that their average lifetime is likely no less than 10 to the power of 34 years. Interestingly, this limit does not rule out the possibility of grand unification. Depending on the specific form of the theory, the predicted proton lifetime falls within a range from 10 to the power of 30 to 10 to the power of 36 years. So there is still a chance, and if a proton decay signal is ever found, it would be a strong argument in favor of the possibility of grand unification. And if that happens, there would be just one major step left to a theory of everything. The step would be unifying it with gravity. Calling it a theory of everything is a bit of a stretch. As I mentioned earlier, we'd first need to develop a quantum theory of gravity, which we don't have yet. Further theoretical calculations show that the possible unification with gravity would occur at even higher energies, around 10 to the power of 19 giga-electronvolts. To confirm this, you'd need a particle accelerator almost the size of a galaxy. Alright, so how does all of that affect us? Honestly, not much at all. Yes, we know that at least 2 of the 4 fundamental interactions are apparently manifestations of a single force. But even here, the energies and temperatures required, conditions under which the 2 interactions act as one, would utterly incinerate us, to say the least. So for us, it's actually a good thing that the forces of nature currently act separately. However, the possibility that the universe operates on a fundamentally simpler level than it seems keeps scientists up at night. And it's quite possible that even in our lifetime, some revolutionary discoveries will be made in this area. Thanks for watching. Links to all of the sources are as always down below in the description. And if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye.